Morning, everybody, and welcome to Physics 4B. Today is May 11th, and today's lecture is going to cover the topic of inductors, basically, induction. So we're going to introduce new devices today, and let's see how we can do that, okay? So let me share the screen. If I can open it first. So again, up to this point, basically, we were dealing with, at least we introduced a couple of the devices. And the two devices are a capacitor and a resistor at this point. Today, we're going to introduce a new device, and that device is going to be called an inductor. Hopefully, by the end of the day, we'll be doing at least circuits involving this device inductor. The inductor is similar in a sense to a capacitor. And actually, let me stop sharing quickly the screen. Actually, I'm going to push that analogy a lot, and you will see it today, that there is actually a one-to-one correspondence between the capacitor in terms of what is used for. Capacitor actually is used to store energy by putting charges in it. It turns out the inductor also is a device to store energy in it too, by storing actually not charges in it, but rather current in it. If you guys are curious, trying to see how an inductor would look like in a circuit, I have one in here. This is the one, actually. That is an inductor. There is another one in here, which is an inductor. There is one that probably you can see in the back of this device is in here, actually. That's actually an inductor, and there is another one behind it. All of this are inductors. There is one in here behind the capacitor that is also an inductor. There is a bunch of places that you can use inductors in. This is actually a device that sends and receives signals, and that's why you have to have these devices in it. And you will see today, hopefully, the LC circuit. I don't know if we can get to it or not, but you will see the LC circuit as being an oscillator. And these are oscillators. So you need some sort of oscillations to synchronize your signal with that of the transmitting point. So what you have in here, you have an LNB receiver basically somewhere, and there is a cable that connects to it, which is a coaxial cable. And the coaxial cable takes that signal and transforms it and make sure it's in tune with whatever you want to tune into, and then it's going to send it back in here through the HDMI port, as you can clearly see, to some sort of a display device like a TV or monitor or something like that. The point being in here is inductors, which are these devices here and here, are heavily used in electronics just as much as capacitors are. So these are capacitors. Capacitors store energy by putting charges in the circuit. Inductors store energy by actually storing the electricity itself, the current itself, as actually for that form of energy. So let's introduce this topic. Let me go into the screen. Let me share the screen again. So basically, are you guys looking at what it says in here, chapter 30?
Yeah, that's visible.
I can see it too.
Very good. So basically, let me, before I introduce that, there was something that we should have done in chapter 28, but usually I don't do it in chapter 28. I defer it until chapter 30. And that is trying to find the magnetic field produced by a solenoid. So let me draw a solenoid. Not like that. That's not a good solenoid. This one. So solenoid is some sort of a cylinder. I'm going to, yeah, let me grab a line in here and make a straight line. Control C this, Control V this, and then move it all the way up next to its counterpart. So think of this one as some sort of a cylinder, okay? Or when you're done using the kitchen towels, basically kitchen paper towels, and the inside, the cardboard inside is the one that we're talking about in here. So let me copy this again and paste it all the way to the bottom. So this is basically in a nutshell what I'm looking at in here. So I assume that you guys have already a piece of paper, whether you're live or watching the recording, and your notes are ready, and you're actually writing and drawing this design with me, because this is not a spectator sport. You're supposed to do things in this class. So this is what I'm going to do. I'm going to change the color just to see how things look like, that's all. I'm going to take this. A wire like this one. This is actually a very heavy gauge. This is 22 gauge wire. This is too thick. It's not going to work well. So you need actually 32 gauge or 28 gauge at least. So we're going to take a wire and wrap it around this cylinder. So you're imagining what's happening behind this wire. And then at the end in here. So I'm going to send a current in this direction to make life easy on myself. So the current is coming here, and it's going to come out from the other side, I. Okay. So on this side, it's going this way. It's going to curl around the cardboard and come back again in this way, in all of these directions. So the current is going actually counterclockwise. When you think about it, the current is going counterclockwise in this loop, and then coming from the other. Obviously, this doesn't end. There is a battery somewhere and probably a resistor and stuff like that I'm not showing in here. The cross section in here for this one is going to be A. So this area is A, okay? The length through which I'm doing this is L. And you have to use the lowercase l, okay? Because there will be a big L that is going to be used in this up to this point. The way I stack these turns is the turn density, or how many turns are per unit length. So basically, this is the number of turns. And this is the length of the solenoid. So this is a solenoid, by the way. So this is a solenoid. And I'm trying to find the magnetic field created by this current. That's basically in a nutshell what the whole thing is, okay? So I want to find what the B outside is. I want to find what the B inside is, created by this wire. And I want to find, again, B out should be B out in here. So that is something that I want to know. That is the whole purpose of this exercise, trying to see how much magnetic field I can create with this solenoid. If I have a current I, obviously current I will create a magnetic field. So what I'm going to do in here, I'm going to use Ampere's law, that's from chapter 28, that says the circulation of the magnetic field over a closed path, dia, is equal to mu naught times the sum of the currents enclosed. That's basically Ampere's law. So we're going to use Ampere's law to find what the magnetic field is outside, what the magnetic field is inside, and what the magnetic field is outside on the other side. There is an assumption that I'm going to make in here, and that is a very long solenoid, very long solenoid, meaning L is very, very large compared to A, or the square root of A to be more, the radius R, okay, compared to R, okay, this radius. So the length is very long. That's basically in a nutshell with this whole analysis in here, this whole argument in here. So that I don't care about what happened in the edges in here, just immediately next to it, that's all. Immediately near this regional space. So that's all of interest to me. So this is what I'm going to do. I'm going to take this cylinder and cut it along the length, along the diameter of this cylinder. Of course, this is a mathematical cut, because if you really cut it, there will be no current going through it. And if there is no current, there is no magnetic field. So what I'm going to say in here, I'm going to take this wires. So I'm going to take this shape and Control C it and Control V it in here. I have a wire in here. So it's going to be sitting in here. And I'm going to copy this one also, or copy the same thing since I still have it in the it's the same thing in here. So this is basically what this looks like, okay? It looks like this because basically what I'm doing in here, I did a mathematical cut. This is not a real cut. If you cut it really, there will be no current going through it. So this is a half circle here. And there is a half circle also going inside in here. Coming on this side, okay? So that's basically in a nutshell what we have in here. So I have a bunch of this currents and they're going in from this side. So I have to be careful in here. So the current, and I want to go back in here, but I want to. So there is a current going in here, as you can clearly see from the geometry in there. So there is a current going in. There is everywhere on this side is current going in. So I'm going to draw a bunch of them. Of course, I have n of them per unit length, where n is. I have a bunch of them, okay? And then on this side, they're coming out. It's the same currents that are coming out. And that's the same number, actually, the same density, same packing, basically. Now, the question to know is that this is not a real cut, because if you actually do this, there will be no current, end of the story. And if there is no current, there is no magnetic field. So do not cut it actually in actuality and see what's going on inside, because you're getting the wires and there will be no current. So this is a math cut. Okay. So having said that, I want to find the B out. Here is what I'm going to argue in here based on symmetry. Because the current is going into the picture on this side, okay? The current is going into the picture or coming out of the picture. So because it's into the picture or out of the picture, first of all, from the get-go, because we know that the electric field, the magnetic field that's going to be produced is going to be perpendicular to it. So the magnetic field is going to be either going like this or like this, okay, one of the two. It's not going to go into the picture or out of the picture. That is properties of the magnetic field that we discussed from the beginning, okay? Because we're trying to find it somewhere in here in this picture, or somewhere in here, okay? Here is the trouble with it. It cannot be going this way, because again, if I want to find it in here, the magnetic field then in this case would lose the symmetry that we have had in there. So in other words, the magnetic field always curls around the current. Since the current is going into the picture, into the screen, so if I argue by that, so in this case, it's going to curl counterclockwise. So it's going to be going like this, up, and coming down this way. So that is the only explanation for it. If you're worried about this one coming out, again, it's coming out of the screen. It's the same thing. On the left-hand side, it's going up, and the right-hand side, it's going down. So that is basically what the magnetic field is going to do for either part of the circuit. So the magnetic field inside is going to be pointing upward. So this would be where the needle will point toward. So this will be the north, and this will be the south. Okay, the magnetic field inside the magnet points in the opposite direction, actually, not from north to south, from south to north. Anyway, so this is the direction of the magnetic field B. So it's not this, it cannot be this, because again, use the right-hand rule and you're going to see it. And it cannot be in any other direction. That's the only two directions that are acceptable in here. So what I'm going to do in here to find it, I'm going to go outside. First, try to focus on B out first. B out. So there is a B out somewhere in here, magnetic field outside. So what I'm going to do in here, I'm going to take an Amperian loop that looks like this. So an Amperian loop of width W and of depth D, okay? Where W and D are arbitrary. I chose them, okay? They're not really part of the problem. So this is an Amperian loop because we want to use Ampere's law, and for that we need to make choices in here. Obviously, the answer should not depend on W or D. It should be independent of both, okay? Because D and W are made up. So the answer should not depend on that. So that is basically what we're going to say. And we're going to say the circulation of the magnetic field, of course, it has to go clockwise, I mean counterclockwise to be positive. The circulation along this path of width W and depth D must be equal to the currents enclosed times mu naught. Now, how much current is enclosed in here? How much I enclosed in here? Equals to what? Do I have any currents in there?
Inside, as in from the inside of the solenoid itself?
Forget about the solenoid. We are outside of the solenoid. We are in this loop. This is where we are right now. It's a made-up loop, okay?
Mhm.
How much current do I have inside in here in this loop? Or do I have any at all?
Um,
Do you see any currents in there?
no.
So the current enclosed is 0.
Oh.
So there is no current enclosed. Okay, very good.
Yep.
Everybody's okay. So there is no current enclosed, so we're in good shape. Okay, so we're in good shape. The magnetic field in here, I just argued it has to be. I'm sorry. The magnetic field in here has to be. Actually, I argued that the magnetic field needs to be pointing down both ways. Okay, so both sides have to be pointing down because everywhere outside has to be pointing down. So that was actually an initial argument, initial point I was making. So both of them, the B out on this side and the B out on the other side, both of them point downward, okay? If I'm circulating in this direction, then this magnetic field is inside, I mean going down, this is 2, B2 is going down, and the circulation is up. So in this case, the dot product of this vector times the circulation is going to be a positive, that's all. I mean negative. Negative B2 times W, because I'm assuming that the magnetic field has to be the same value everywhere at this this distance and everywhere at distance. You say, why it has to be the same? Well, because this is an infinite solenoid. If you tell me there is a value in here that is different from the value in here, all I have to do is shift it up and down. And because it's an infinite solenoid, then in this case, you shouldn't see any difference because of symmetry. But you will see a difference if there is difference in values. So B1 here and B1 here is the same value everywhere, at least as the same distance from the solenoid. Same thing. B2 in here should be the same value whether I am here or here. So this value in here is constant along this length. And this value is constant along this length. But they may be different, the values. In here, the magnetic field, they just argued that's actually pointing down. And the circulation is along this path. So in this case, there is a cosine of 90 degrees and cosine of 90 degrees is 0. So the dot product here is going to give me 0. The dot product also is going to give me 0 because there's circulation in this way, and there is a 90 degree between them. So in this case, it's going to also give me 0. So at the end of the day, this path integral, which is going to be 3 integrals, is equal to 0 on the other side. We just argued there is no current inside. So on one side, it's equal to mu naught times 0, which is 0. On the other side, it's equal to B1 is in the same direction of the circulation, so it's B1 times W. And plus 0. If you want to, we can write 0. Plus, this one is actually negative because the circulation is still counterclockwise and the magnetic field is still pointing downward. So this is minus B2 times W. And this one is actually 0 too because they are perpendicular to one another. So again, cancel the W from both sides. So what this is telling me is that B1 is the same as B2 outside. So the magnetic field, it doesn't matter how far you are from the solenoid, it's the same value, regardless of how far you are. As long as it's an infinite solenoid. Now the point being in here is I just know that far away from the solenoid, there should be no effect of the solenoid on the infinity. So B far, B at infinity, must be equal to 0. Since it's the same value everywhere outside, so everywhere outside must be 0. So B out must be 0. So the magnetic field outside of the solenoid is 0. That is basically in a nutshell what this is. And it's the same thing in here too. You make the same case based on the same analysis in here and in there, you're going to find 0 magnetic field. So the magnetic field, if it exists, is going to be inside the solenoid. End of the story. So this is the B inside that must be a value. So this is all the B there is to it, okay? And there must be a B everywhere in here, okay, in this region of space. So we're going to find that B inside. Now we're going to call it B because there is no B outside. So the only B that is left is the one inside the solenoid. So let's do that then. Let's take another Gaussian, I'm sorry, my mind is still in the Gauss's law. Amperian loop. And here is the Amperian loop I'm going to choose now. I know the value outside is 0. I just made the case for it. So B out in here is 0. So there is no circulation. So I'm going to go from this side, again on this side, and here is B is 0. So we don't care for it. And in here also is 0. But the minute we trespass in here, the magnetic field is pointing upward and the circulation is in this direction. So there is a cosine of 90 degrees again. So there is a contribution of 0 in here too. And there is a contribution also of 0 in here too, because of the same 90-degree angle also. But there is a value in here. Since I'm coming down in this side, and the magnetic field I just argued must be pointing up. So there is a negative value in here because of the dot product. The magnetic field is pointing up and the circulation is still counterclockwise. So it's still in that same direction. So on one side, it's minus B times W, plus 0, plus 0, plus 0, plus 0, plus 0. So it's minus B times W plus 0 because they are perpendicular in here. There is a magnetic field in there, and it may be different than this B. But the point with it in here is that it's perpendicular to the circulation. I'm going to write it 0. Why? Because cosine of 90 degrees is 0. Okay. Plus, this whole region is 0. This one is 0, this one is 0, and this one is 0. Why? Because there is no B there. So B times this length, even though they're perpendicular, it doesn't matter. It's 0 anyway. Times 0 times this number, 0 times this number. So this is 0. 0. Because B out, I just make the case for it is 0. We're outside. Plus, the same thing in here, the vector B and the displacement in this case for the circulation is 0. So that is 0 because, again, the same reason, cosine of 270 degrees is actually equal to 0. Same thing, which is 90 degrees, okay? That is equal to 0. This whole thing must be equal to mu naught times the current enclosed. How much current do I have enclosed? Do I have 0 currents now, or do I have currents? Is this similar to this situation now? Do I have currents now?
I think you should have currents now.
Yeah, they are this arrows that are going into the picture. Those are the currents enclosed.
Mhm.
And they are first of all negative because they are going into the picture. Okay?
Ah, okay. Yeah.
Okay, so we have a bunch of them and they are all negative. So I have a minus mu naught times, okay, how many do I have? If each and every one of them carries a current I, and I have W, and I have N per unit length. Remember, N was the number of packing per unit length. Okay, but I don't have a unit length. I have a W length, actually. I have a W in here. It's the same W in here. So I have actually their number should be N, should be their density times the width in this case. So this is how many actual wires are going, depending on how well I wrap them. Look at this way this is wrapped. So this is a very important property of the inductor. This is actually an inductor. So in this case, I need to know how they're wrapped, but I brought a W width, which is again a part of the Amperian loop, which should not depend on the answer. So the answer should not depend on W. It would be a disaster if the answer depends on W. So I'm going to do in here is the number, which is just their density times W, times each and every one of them is I. So this is the current enclosed. And the negative sign is due to the fact that they're going into the picture. Remember, anything coming out is positive, anything going in is negative. So if we do that, 0 plus 0 plus 0 is 0. And the W cancels. That's good, actually, that it cancels. That's very important. More important than the negative sign, because the negative sign, you can work your way through it and make a case that maybe you chose the wrong direction and things like that. But the W is not a property of the problem. W is something outside of, it's made up. It's not real. W and that D, properties of the Amperian loop, just like the Gaussian surface, are not real. So in this case, the answer should not depend on them, and it does not. It depends on N, which is how well you wrap this wire around the solenoid, how well you pack them. That is important. Other than that, and probably the current also, because if you don't have current, you don't have magnetism. And the medium that you have in there, which I assume to be vacuum, that's why I use mu naught. If it was a different material, I'm going to use the mu for that material. Okay. So that is basically how the magnetic field is calculated. So again, I'm going to go back and to cancel the negative sign, which is actually important because my signs were correct. So that means B is equal to mu naught N times I. This is a very important result for a solenoid. Actually, a very important result for a solenoid. So this is the magnetic field inside a solenoid of N turns per unit length. Okay. That's a very important result. There is another type of solenoid, which is actually in a toroid, like a donut, basically. Think of it, take a donut and wrap a wire around it. Go back into the same wire in here. Of course, you have to take only one of them. You can take both colors and wrap it around the donut. So let me draw a donut in here, because you will see that a lot also in circuitry too. Actually, I'm sorry. That's what this shape, the one that you have before you actually is. So let me select it and put it inside and shrink its size a little from one side and the other side. And now I have what looks like a donut, okay? It's a little bit eccentric because of the fact that I'm looking at it in angle. It should be really a round donut in here. Okay, let's draw it a circle, okay? Because it doesn't look too good. So let's cut it into a circle. Okay. Still kind of has some sort of a shape in here. I mean, when you cut it, it looks like a circle, okay? So it's not really a circle, so it's 3D object, okay? Again, when you run the wires around it, it's going to be, so think of it, this is the wire, comes in here, and you wrap it this way, and you wrap it this way. So you're turning the wire around it. So it's like a tire, really, okay? Make sure you do a better job when you draw this one on your computer, on your with a pencil or a pen or something like that, because this thing in here, and the last one it comes out, it's going to come out this way. Again, I will try to make it so that it's going in a counterclockwise direction. Counterclockwise direction, meaning the current is going this way, actually. Is this? Yep, that's correct. So everywhere in here, it's going like this. And it's coming on here. So it's going around and around and coming from the other end. So there is a current I that is running through this one. But instead of packing it that way, I know exactly how many of them. So there are N turns now. And the inner radius, I'm going to call it R1. And the outer radius, I'm going to call it R2. Okay? And I want to find the magnetic field produced by this solenoid. Again, I want to find it inside the tire and outside of the tire and in the rim itself, in this section in here. I want to find all of these. So B in the inner part, B in the outer part, and B inside. So this is my focus in here. By symmetry, it should have like that. That symmetry in there, that spherical symmetry in here, that depends on the radius. So again, I'm going to make a mathematical cut in this, so it's not a real cut, so don't do it, because if you really cut this thing in here, you're going to lose your magnet. Okay, so I'm going to copy that, and I'm going to move it down. So hopefully, I know you don't have cut and paste, but somehow you can draw these things on the fly for your case. Come on. Let me copy this thing in here and paste this in here and bring it inside. I know that's probably have better drawing tool. It looks better. Anyway, so I'm going to come in here. Obviously, this region is very, very close from one another. So what I'm going to say in here, this is how it looks like. Now, the number of turns inside is the same number of turns outside. So the magnetic field, you can clearly, the current you can clearly see is going out from the inside and it's coming out from the inside. So it's going in from the outside. So it's going in, in, and I need to draw as many inside as many outside. So really, there should be an exact number of them, because the difference in radius, they will be further spaced outside than the inside. Inside, so these are coming out, all of them. Okay, so that is how the cut. Again, this is not a real cut. This is a mathematical cut, because if you actually do this, you're going to cut the current, and this is not going to work. So you really need the current in that. So here is the argument in here. First of all, inside, I'm going to make an Amperian loop, which is just a circle of radius r. So r is not real. R is basically at this point. No, R is real, because I want to find the magnetic field in here. Again, here is the argument for the magnetic field, how it should point. The electric field should be coming in or out of the picture. Okay? So if it's coming out of the picture, it needs to circulate in a fashion around this one. So it has to actually go this way, to go around this portion and another portion, another. But it's going to be zero. Can anybody tell me why it should be zero, the magnetic field inside? In other words, how much current is enclosed in here, in this blue circle? Or do I have any currents at all enclosed in that circle? Of radius r less than r1. Do I have any currents in here?
I do not think you would have any currents.
So I is equal to 0. Does everybody agree with Byron? Yes, no, maybe? Because the current's enclosed there in here, and we are in radius less. Can you see that the current enclosed now is 0? Everybody else? Good. Come on, guys. Is there any current enclosed inside that circle, the blue circle? Yes, no, maybe. This is not a democracy, by the way. Everybody has to have an opinion in here. And it doesn't matter, right or wrong. Do I have any current enclosed?
Yes. Wouldn't we have a current enclosed in the
Blue circle. Do I have, in the blue circle, do I have anything inside? The currents are drawn in red, okay? In this circle, in here. Yes,
Yes.
no, maybe. Do I have a
Yes.
current in here?
You should, because the current.
They're outside. They're outside of the circle.
Oh, then no, sorry.
Okay. 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 So basically, in this case, there is no current enclosed. So if I apply Ampere's law, it says the circulation around this circle, which it should be the circumference times b. So at some point, it's 2 pi r times b. This must be equal to the current enclosed, which is 0 times mu naught. So the only way for this one to be 0 is for b to be 0. So b inside is 0, basically. So there is no magnetic field in this region. I'm going to take it completely way outside in this circle of radius r, which is bigger than the bigger of the two radii. And now there is definitely current enclosed, but it's the same number that come out, the same number that go in. So the enclosed in this case is going to be, when I do this algebraic sum, is going to be what? Some of them are positive, some of them are negative, and they're exactly the same number. Because the same wire that wraps in, goes out, it comes out on the other side. It's the same wire. So how much current enclosed in this outer shell now, in this outer circle? The net one. If 5 come out, so they're positive 5, 5 will go in too, so they're negative 5. How much the sum should be then?
The sum should be 0.
Absolutely. Okay. So in this case, if I apply Ampere's law, it says the circulation of the magnetic field, which is just B times this big circumference of radius R, which is bigger than the bigger of the two radii, then in this case is going to be B times 2 pi R. Well, that's what the circumference is, must be equal mu naught times the current enclosed, and the current enclosed is 0. So it's going to be 0. That too will make that the magnetic field way outside is 0 too. So the magnetic field, if it exists only in this circle of radius R that is less than the big R2, but greater than R1. So now I definitely have currents enclosed, and they are these currents, okay? But I just said that I have n turns, so there are actually n of them. So on one side, it says, let's see the circulation now. The currents are coming out. So the circulation is going to be counterclockwise. So the magnetic field will be in this direction, okay? And the circulation also is going to be counterclockwise. So I have pi times the circumference, which is 2 pi r of the circle, must be equal to mu naught times the current enclosed, and there are n of them, and each one of them is an I. So there is this many, so that is the current enclosed inside this type of geometry, mu naught times n over 2 pi r times I. With a little bit of math, you can argue that n over 2 pi r is actually the density packing in this case, because the circumference on how many wires you put in, and the formula looks awfully similar to this one too, actually, if you define the density as being, in that case, n over 2 pi r, instead of just n divided by L. But this is the actual magnetic field inside solenoid. So this device too traps the magnetic field. So in a similar sense, the capacitor traps the electric field, the solenoid traps the magnetic field. End of the story. So that is basically what this whole exercise is. And if you're curious trying to find its value, here its value in this kind of toroidal solenoid, or here is value in the case of a cylindrical solenoid. So this is actually cylindrical solenoid. What is the value? Mu naught times the packing, which is how many turns you have per meter, times the current that runs through each and every one of them. That is the magnetic field that you have in there. If you're trying to find the flux of the magnetic field, the flux of the magnetic field in this case would be just B times the area A. Okay? The flux of the magnetic field in this case, there is a problem, first of all, it depends on R. The magnetic field closer by is stronger than the magnetic field further out, because it's 1 over R in here. But you can take an average if these two values are very close from one another. You can just take the middle one as being the magnetic field inside this type of solenoid. This is heavily used actually in the industry. This type of solenoid used a lot, okay? So in transformers, for example, they use that. So this is a transformer that uses that type of packing. Okay, so this is I lifted from a device in here that I had. So as a matter of fact, let's introduce the transformer, which is really part of this chapter now. So now we're done with the stuff that we need to catch up with. So this is a device that I'm going to draw now. So let me see if I can get into the, no, I don't want to do that. Can it take the lasso tool in here and select everything in here? Including that is fine. Control C, because we need it in here right away. Control V. I want it there. Control Z. I want it in here actually. Okay. So this is the solenoid we have in here. So we know its magnetic field. If I have a current running through it, So let me select this stuff in here and delete them out. And I need the area actually. Care about the so this is the solenoid. We just found its magnetic field that it's produced. But instead of doing that, I'm going to take another wire. Conveniently, next to me there was a wire with two different colors. Okay, so I'm going to take another wire. They don't have to have necessarily different color, but just for my taste, I'm going to have them in different colors. So I'm going to wrap this wire differently. So I'm going to take this wire as it comes out from the other side. I'm going to run it here, actually, as you can clearly see. They're not touching, they're protected, okay? So don't think that there is a crossover between the wires in here. When it comes in here, I'm gonna wrap it around again. When it comes out from here, and that's enough, okay? So when it comes out from this side, I'm going to take it out, okay? The packing on the first one. So now I have to be careful with the labeling. So the red, I'm going to call it a current I1. And the number of turns in this case is going to be N1. And this length is still L. Okay. The blue one, I'm going to say the number of turns is N2, where N1 is not necessarily equal to N2. Okay. Then, if there's a current in the primary, so this is called the primary, okay? And this is secondary, just because of the way these letters are labeled. So this is called the primary, and this is called the secondary. Okay, so this is transformer now. So if there is a current in the primary, it's going to create a magnetic field. How much magnetic field? Well, it's easy. It's B equals to mu naught times N1 over L, because I have to be careful now, times I1. Okay, that's how much magnetic field is in there. As a matter of fact, it has a flux that I can find. The flux of the magnetic field is going to be just B times A. And this is B, I mean, this is the magnetic field, and this is the cross section. So there is a flux in there. If that flux changes with time, it's a condition, then there will be an EMF in the secondary, which is equal to just minus, there is a flux in here per turn, but I have N2 turns. So there will be an N2 times this flux per turn. This is called the coupling flux, okay? The flux that joins both of them, that goes through all of the areas, actually. Since you have N2 of them, each and every one of them acts like its own battery, having its own EMF, which is minus d5b over dt, and take that, you have N2 of them, and you connect them in series with one another. Now you have a bunch of batteries. So this is the battery in here. If you connect these wires, if you connect them, actually, there would be a current that is going to flow in this direction, okay? There will be an I2 running through this circuit if you connect them. If you don't connect them, there will be just an EMF in here, and that's the end of it, okay? So you have an EMF in the secondary, okay? Actually, there is a voltage in here, and that voltage, I'm going to call it V2, which is just the EMF in here, whether you connect it or not. So there is a voltage in here. And whether or not, wherever the battery is, if there is a resistor in here, and whatever, so there is a voltage in here, which I'm going to call it V1. And that V1 is actually equal, must be compensating for the EMF that is going to be established in here. And that EMF is actually also due to Faraday's law. That EMF due to the primary is actually going to be in a similar fashion that needs to be overcome by electrostatic forces, by electrostatic energy in here, must be equal to minus N1 now, because I have an N1 turns now, okay, on this side. Each and every one of them is acting as if its own battery, and somehow the magnetic field is changing with time. And if the magnetic field is changing with time, it's due just to this current. So it doesn't matter who caused whatever changes in it. So if there is a change in the magnetic field, there is a change in its flux, and that change in the flux will translate also into this EMF. I'm sorry, d5b over dt. Now, So there is a voltage in here in the secondary, and there is a voltage in the primary, and the ratio of these two voltages, because the coupling flux in this case is the same value. So if I take the ratio, all I'm left with is N2 over N1, that's all. Okay? So in this case, and the negative cancels the negative, by the way. So in this case, V2 over V1, the voltage in the secondary over the voltage in the primary, is simply equal to the number of turns in the secondary over the number of turns in the primary. That's all. That's all there is to it. So now I can find the voltage in the secondary if I know what the voltage in the primary is by doing this expression here. If I start, for example, with in the primary for 120 volts, and I need a power for my cell phone of 5 volts, I need to cook this number so that it's equal to 5 over 120, because the 100 cancel 100, and then I will end up with that. So this is the number of turns in the secondary. This is the number of turns in the primary. So the primary needs to have more turns in it than in the secondary. Then I have dropped the voltage from 120 volts, the one sitting across this edge, down to 5 volts, what my cell phone requires. Let's say, for example, I have another device. I have my laptop. It requires 20 volts to operate, and there is still 120 volts on the other side. I need to have the ratio of 20 over 120 in here. So the 120, so I need to have in the secondary actually 120 volts versus every 120 volt in the primary. So in this case, I dropped the voltage successfully from 120 volt down to 20 volt. In both of these examples, when N2 is less than N1, it's called a step-down transformer. If N2 over N1 is less than 1, this is actually a step-down transformer. This is the #1 transformer that is found in households, common household item. Every charger, okay, that you have in your household is of this type. And the number of turns in the charger itself, which is connecting the wall to your device, there is just enough turns in there in the primary versus the secondary in such a way that this ratio will give you the exact voltage that is required for your device. If you mess around with turns, you're going to get either less voltage than what your device requires, or more voltage than what the device requires. In the first case, it won't work. In the second case, probably you're going to damage it. Okay. So the transformer is a very important aspect of it, and the only way it works if this current actually changes with time, and an AC current. Because if the current is not AC, the flux of the magnetic field does not change with time. And if it doesn't change with time, there will be no EMF. So there will be no transformation in voltage here. So the condition for a working transformer is that it needs to be in an AC circuit. If you go back into this device in here, when I was showing you earlier, this is where the power supply comes in here. If you look at next to it, there is actually a transformer in there, okay? And there is actually, what you call them, capacitors also. Near power supplies, most of the time you will find a small device like this one. This is actually more obvious, okay? More obvious than the first one. Let me turn off the sharing screen so that you guys can see it improved. You see, I don't know. You see there are 2 legs in here under my finger, and there are 2 legs in here too. So each and every one of them is actually a primary and a secondary, okay? So if this is your primary, this is your secondary, and vice versa, okay? So again, this is the transformer, and it's required actually part of the electronics in here. It does not use the air inside. It uses this piece of iron in here, which improves on the mu. So now it improves on the flux. So if the current changes even slightly, so it's going to capture it, okay? So this is actually a device that is extensively used in electronics. Obviously, once the current passes that point, it needs to be regulated, and that's sometimes you have transistors and things like that to fix the current and make it into a steady DC current. So this is how electronics usually works. Obviously, as I was saying in the intro, this is actually a special case. You will have more inductors in it because of the fact this is an oscillator, this special device. And like, for example, an Arduino in here, which should not have a bunch of them, if any at all, because of the fact this does not oscillate. This is not a This does not require, especially this is a modern device, okay? Here is another one with a big transformer in it, okay? This whole thing is actually a transformer. Okay, this is actually, there's a lot of capacitors also and resistors. I don't know if you can see them or not in here. Okay, so this is an outdated equipment in here. It does not use as much microelectronics as modern equipment is. Anyway, so let me go back into the sharing the screen. So we learned the step-down transformer. If I take this transformer and reverse the polarity, connect the source in here and the out in here, that's going to be step-up transformer. In other words, if I have 5 volts, I can make 120 volt out of it. So step-down transformer can be actually reversed to make it into a step-up transformer. So if N2 actually over N1 is more than 1, this is actually called the step-up transformer. This is usually used by the power company. Step-up transformer takes low voltages and bring them up before delivering them on power lines to the consumers. So they are actually a handy way of delivering it. Does it matter in terms of energy? Would you gain more energy? Absolutely not. Because if you increase the voltage, you drop down the current. And remember, the power is still the voltage times I, so the power is always VI. So if this goes up, this must go down, and vice versa. That's why you have to protect your electronics from the high current that's going to emerge. So immediately you have to consume that with a resistor. That's why you need the resistors in there to tame those currents that come out from there, okay? So it's really important to manage your circuitry in here. Otherwise, you'll have high currents coming from it. Although you step down the voltage, you have it 5 volt, but the current now went up, okay? So the power is always VI. So it's true in this case. The power does not change. So you're not going to get energy from a step-up transformer. You get more voltage, but the end of it, that's power is still the same at best, because it's going to lose power due to Joule heating anyway. So it's going to be less than 1, okay? So that actually, as a matter of fact, if you touch any of your chargers, you would see it warm after a while. It's hot after a while because of the fact that you have Joule heating in it. So it's going to overheat. It's going to deliver less power than what it takes, okay? And even if you unplug it from the computer and you have it just plugged into the wall, it stays hot because there is a current running through the primary still, okay? Although the secondary, in this case, there is no current in it because you unplugged it from your phone or from your charger, from your computer, whatever that is. So there is always current in the primary in this case, albeit in here it's disconnected. Although now modern, basically, chargers, they have this safety feature in here. If they notice that this is disconnected, they disconnect the current in here immediately, okay? Anyway, so this is enough about transformers. I think we have introduced them plenty. Let me talk another property in here between the transformers, which is the mutual inductance. Let me explain what's going on in here. There is a flux in the secondary. And the flux in the secondary is due to the magnetic field produced in the primary. So again, there is a magnetic field produced in the primary. So I1, that will lead to a magnetic field in the primary. That magnetic field would lead to a flux that joins them. That will lead to a flux in the secondary. So what I can say in here is the flux in the secondary must be connected to the current in the primary. And we call that the mutual inductance, okay? So what's going on in here? We have current in the primary, regardless of whether or not that current changes with time or not. You will have a flux in the secondary because, look at it this way. The current in the primary will create its own magnetic field. If I multiply the magnetic field by the cross-section A, I have a flux in the entire region. I mean, I have a flux in the entire region, yes. And that flux, among other things, is running through the secondary, the blue lines. So how much flux I have in the secondary? It really depends on how much flux, how much current is in the primary. So this connection between the two is expressed in terms of what is known as the mutual inductance. You might say the same thing. Okay, if I have a current in the secondary, I would have a flux in the primary, and it's true. And then the mutual inductance then is a connection between the primary and the secondary. I mean, the secondary and primary, I should say. Okay. There is a theorem in mathematics that I'm not going to prove in here. It's actually, its proof is a little long, where the two mutual fluxes are the same, because it just depends on the overlap region between them. And that is a geometry that is common to both of them. And you can show that the mutual flux between them is the same. In other words, I drop the indices 1, 2, and 2, 1, and just call it the mutual inductance. Okay. So this is by definition what the mutual inductance is. The fact that a current in one side of a circuit will impact the other side of the circuit by creating a flux in it. So mutual inductance you have to have a primary and secondary, is the effects of one section of a circuit via its current on the flux in another region of a circuit. That is basically what it is. So that's by definition, if you wish. Okay. So what are the units in here? The units of the flux are equal to the units of the mutual inductance times the units of the current, and the units of the current are the amp. The unit of the flux is magnetic field times area. So it's a Tesla times meter squared. Okay. And the magnetic field, if you guys remember from the expression that F equals to QVB, the units of the magnetic field, which is a Tesla times a meter divided by second times a Coulomb, and a Coulomb is not a fundamental unit, by the way. It's an area, a second times an amp, so it's in a second, is equal to the units of the force, and the units of the force are equal to Newton, which is kilogram meter per second squared. Cancel the meter, cancel the meter, cancel the second squared, cancel the second squared, and one of the seconds goes in here. And that gives me the Tesla has the units of a kilogram. It's not really a fundamental unit. That's my point in here. The Tesla is actually a derived unit, just like the Newton is. Okay, so it's a kilogram divided by an ampere in second squared, because one of the seconds remains with the other second. So this is the Tesla, actually. So the Tesla, I can sub it for its values. And now I have the mutual inductance, which is going to be equal to a kilogram divided by an amp times a second squared times a meter squared. So that is what the Tesla is, because you have a meter squared times everything, divided by another amp in here, which is going to be an amp squared. So it's a kilogram, meter squared, amp squared, second squared. We will get sick and tired of calling it that way. So we gave it a name. We gave it the name of Henry. So this whole thing is a Henry. So the units of the mutual inductance is a Henry, okay, the H. Typical inductances are of the order of few millihenries, okay? If you look at the devices that you required for the labs and things like that, usually it's 47 Henry and millihenry or something like that, okay? So this is a typical number for the inductance, okay? So that is the inductance in here. It's very important to see how we can calculate the mutual inductance in this case, but it's fine. I mean, we can calculate it. Yeah, let's find it in here, okay? Let's find it in this case, in this special case in here. Okay. Because we have the magnetic field B. We just found it. It's mu naught. We know what the magnetic field in here in this case is. And mu naught times N divided by L. It's N1 divided by L. Times the current I, which is in the primary, I1, okay? So this is the magnetic field created by the primary. Now, the flux phi B is going to be equal to, in this case, this is the connecting flux that goes around through each and every one of those turns, is going to be mu naught times N1 divided by L times the area times I1. It's basically the flux, the magnetic field times A. It's BA, okay? Now this is a flux, this is a joining flux, but I need to find the actual flux in the secondary. The actual flux in the secondary which is phi2, which is just N2 times phi b. So it's going to be just mu naught times N1 times N2 divided by L times A times I1. So that is actually the flux. And the flux by definition is M times I1. So M in this case will be just whatever is in front of I1 in there. So the mutual inductance in this scenario is going to be mu naught times the number of turns N1 over N2 divided by L times A. It's clear that mu N12 is equal to mu 21 in this case, because all you do is just change the order of N1 times N2, that's all. And this is the same number. So you can clearly see that mutual inductance of M12 is equal to mu M21, because all you do in this case is switch the order of the number of turns in the primary and the number of turns in the secondary. And L is the same common length for both of them with the solenoid, and A is the cross-section that is common for both of them, and mu naught is the material that is sitting inside that solenoid. So we were able to find M, similar to the case when we were able to find the capacitance actually for a parallel plate capacitor. So this is in a sense similar to that. So we were able to find C then. Now here it's M, the mutual inductance. So plug in the numbers in here and you have an M in Henry, how much you need, okay? So this is really the way you find it in here. Okay, let me introduce now how much time we have. We still have time. So let me introduce the self-inductors. The self-inductance is a special case though, of the mutual inductance. You have a wire that is wrapped around itself, and that's it. So if you have a current running through it, it's going to create its own magnetic field. When you multiply it by the area, you're going to find the joining basically magnetic field in here for that wire with itself. And you're going to multiply it by N and the area in this case to find the flux, and you multiply it by N again, and you're going to find the flux that is actually opposing this whole thing. So the flux in this case is going to be L by definition, not M, times I, where L in this case is the self-inductance. We don't call it self-inductance anymore, we just call it plain inductance. This is called an inductance. I know we call the other one mutual, but this one we call it inductance by itself. You have to understand that L in this case is actually the inductance of a wire with itself. So the fact that you have a wire wrapped around somehow in here will produce actually an effect, an undesirable effect, or sometimes desirable effect by itself. So you really don't need a transformer to have an inductance in here. You can do it by itself because the current, as it changes, and it creates a magnetic field in this region. And as that magnetic field is created, and if the current is changing with time, that is going to induce an EMF in here that is going to be inside this one that is going to oppose the changes in the flux. So it's the same thing, except that it's within itself only. That's all. This case is called an inductor, as opposed to transformer. So this is an inductor, a self-inductor or an inductor, end of the story. So this is what the inductor is. So L has the same units as an M actually, because it's a flux divided by current. I can go through the same exercise and show that L has the same dimension as a mutual inductance, which is a Henry, okay? So those are the same units for L. Actually, this is a far more important device in electronics than the transformer. Transformer usually near the power supply, but then after that, you really don't need it. Most of the time, actually, not always. But the inductor is actually needed all the time in a circuit. And we'll see how we can use it inside the circuit, okay? So this is L. So let's take a solenoid now and try to find its own inductance. So it's going to be N1 is equal to N2 is equal to N. So for a solenoid, N1 is equal to N2, which is just the number of turns N. So it's going to be L in this case is equal to mu naught times N squared divided by L times A. That's the end of it. Just make N1 equal to N2, which is N, the number of turns. So this is for a long solenoid. Think of it as the capacitance too, where we find it to have epsilon naught, and you have sigma, epsilon naught, and you have A over D, the distance between the plates. So this is similar to that. Here is a question. If I changes with time, there will be an EMF in the solenoid, and that EMF will oppose the change in the current, because again, that is the oppose is coming from the Lenz's law, because again, this whole thing is based on Faraday's Lenz's law. So again, the EMF in this case, the voltage across an inductor is that EMF. So this is delta V across an inductor is going to be just minus L times di over dt. Okay. If I does not change with time, there is no voltage across it. But if the current changes, in this case, there will be a magnetic field that changes with time. In other words, the flux changes with time, and the flux changes with time induces basically an EMF to oppose that change. That is coming from Faraday-Lenz law. So this is what the voltage then across the inductor need to be, and the current that is pushing the current in this direction need to at least equal that amount. If it does not, then this thing will kill the current along that path. So this is going to oppose not the current, and I'm going to make a big deal in here, not the current, but the change in current. Because it doesn't care what I is, it cares about what di over dt is. If that is not equal to 0, then there is a voltage. If that is equal to 0, then the current can fly through, it doesn't care. If there is a 10 amp steady going through it, that's fine. There's no problem with it. Try to yank your 10 up in that case, it's not gonna like it. It's going to like to keep the 10 amp going in the same direction. Try to bring it down, it doesn't like that either. It wants to keep the 10 amp going in the same direction. So if somehow there is a solenoid in here, and there is a 10 amp current going in here, try to increase the current a little, it doesn't like it. It wants to keep the current 10 amp going in the same direction. Try to bring it down a little, it's not gonna like it either. It wants to keep the 10 amp going in the same direction. That is what this means, okay? So that is what this whole thing is. And the negative in here is the voltage drop in this direction. If the current is flowing this way, it's going to drop in this direction. That is basically in a nutshell what that is. So, this thing can be useful then to store energy stored in the capacitor. There is a lot to discuss in this chapter. This is one of the richest topics in this class. Energy stored in an inductor. So imagine with me the following scenario. I have a current already, I, running through an inductor. Okay? So there is already a current I running through the inductor, and I want to change it. Need to change it by di over dt amount of time. If we do that, there is a voltage then. And that voltage is going to be an absolute value. We don't care for it right now. It's going to oppose that. That voltage is going to be V equals to L di over dt. This is the opposing voltage. So if I want to do that, I need to overcome this voltage. I need to deliver energy to overcome this voltage. I need to do work to overcome this opposition. And that work is given by the power, at least, with which this thing is delivered, is VI again. Need power P, which is just VI. Okay, that we saw it. That we saw it a long time ago. So this is the power that I need to deliver to do what I want to do, to change the current from I to I plus DI in an amount of time dt. If I want to do that, this is how much power I really need to deliver to overcome this thing in here. So at the end of the day, I have increased the current, if you wish, but I have put that power that I supplied into energy inside the inductor. So I can retrieve it later somehow. Okay, so let's calculate this power. It's obvious from this calculation is simply equal to the power is equal to Li di over dt. That's simply as that, okay? This power is the rate at which I'm delivering work or energy per unit time. This is the energy stored in the inductor at that rate. This is the amount of energy I'm delivering to do that. And it's stored now in the inductor in this form, okay? Obviously, I need to do some calculus stuff in here to find the actual energy. So what I'm going to do in here is note that the derivative with respect to time of 1/2 of I squared is equal to I di over dt. Just using the rule of how to take derivatives in here. The rule of taking derivative of I squared, drop the 2, cancel the 1/2, and then the derivative of I times I itself, because you have an I squared. So this is true, okay? Because of that, then I have an expression for this one, which is this one. And L is constant anyway, so it's going to come in. So what this says then, the rate of storing energy inside the capacitor, which is the power, capacitor inductor, is 1/2 of Li squared is equal to d with respect to t of that energy that's being stored inside the inductor. So this becomes an identity now, okay? Because L is constant, so I just throw it back into the parentheses, okay? So now, if I integrate both sides, then it tells me that the energy inside an inductor is 1/2 of Li squared, okay? So this is the energy inside an inductor. Remember when we did the capacitor, we found the energy inside a capacitor to be Q squared over 2C. This is similar in a sense. I have 1/2, but instead, because there we store charge in it, here we store current in it. Current is actually steady. It doesn't like it to be changed. In there, I have 1 over 2C, 1 over C, and in here I have just L in this case, which is the inductance of this inductor, okay? How does this sound? Because we still have quite a few materials in here to cover in this chapter. Does this sound a lot, or should we continue at least for the next 10 minutes to derive another very important expression? How do you guys feel about it? Because it seems like I have thrown everything at you today.
Yeah,
It was
yeah.
a lot of information. We're gonna have to try to go back and understand it better.
See, it seems like quite a bit to soak up, but yeah.
Yeah. I'm sorry. I know it's coming from angle.
Yeah, that's fine.
Okay, so I'm gonna stop in here for you guys. So hopefully to consume these things next time when we meet, which is gonna be Tuesday morning. Thursday. Today is Tuesday. I'm sorry. Thursday when we meet again, we're gonna pick it up from this point in here, and we're gonna hammer this expression, found the energy density inside an inductor, and compare it to that of the electric, the energy density of the electric field, and then play with the RL circuit, resistor and inductor, and also LC circuit. I think we would be done mostly, because we still have the RLC circuit too. Okay, we have quite a few things. So I'll see you guys Thursday.
Alrighty.
Perfect.
See you Thursday.
Question.
See you Thursday.
When's our next exam?
The next
yeah.
exam should be sometime in June. I forgot the exact date, but you will have plenty of time to prepare for it. Okay?
Okay.
Okay.
Everybody's taking their finals now, so I need to know so we can like mentally prepare myself for it.
Okay, the final is already fixed. Okay, so whatever that date is, it's going to be the Tuesday of June. I think June 8th. I don't know exactly.
Yeah, it was like June 6th or June 8th.
Okay, June. Hold on. Let me give you the exact date for the final. I know it's going to be June 8th, the final.
Okay.
So the last exam either going to be June 1st or June 3rd. I think most likely it's going to be June 3rd. Okay.
Okay. And that's going to be on which chapters?
27 to 20. What is it? 27 through 32. Okay.
7 through 32. Okay.
Okay. Let me say this: Chapter 30 and Chapter 32 are going to represent a major bite from this exam. 30, 31, especially 30 and 31. Okay. Plus 32, they're going to be a big chunk of this exam. Because remember, 27, 28 were just leading to this thing. This is really like when you are basically training yourself getting into this heavy stuff. So I urge you very much that you come in for this 3 chapters, ready to basically pull your sleeves on, get a piece of paper, a pen, and follow every single thing. Because we're going to do AC circuits. And AC circuits are going to be a lot of basically math involved with it. We have options, whether we use complex numbers or use phasors method or use clean trig functions. Okay. So however you guys are ready for it. Okay. Sounds fun?
All right.
All right.
Sounds good.
Yeah.
Okay. See you guys Thursday. Have a
Yep.
good rest of the day.
Same to you. Have a good rest of your day.
Bye.
Thanks. Bye.